zero temperature, the Kelvin energy or Kelvin scale or the energy kinetic energy of the particles must be 0, and this point is at 0 Kelvin. At 0 Kelvin temperature, the kinetic energy of the particles is 0. So the kinetic energy is 0, which means that the particles themselves are not moving, which means that if gas particles are not moving around, then the volume of the gas must be 0, because they are not hitting against the inside wall of the container. So at 0 Kelvin, kinetic energy of the particles will be 0. They're not moving. The gas has no volume. And this actually has not been achieved. Hey guys, sorry about that. My computer is not responding to this podcast very well. I'm gonna let you guys know that scientists were able to get really, really close to absolute 0, which is 0 Kelvin, but they have not been able to achieve it in an experimental setting. So let's talk about the 3 units of temperature. Celsius scale is dependent or was established on the property of water. So at 100 degrees Celsius, water boils. That's my W here. At 0 degrees Celsius, water freezes. However, the Kelvin scale is established in terms of kinetic energy. So as I took a look at the Celsius scale at 0 degrees Celsius, and here's my 100 degrees Celsius. At 100 degrees Celsius, gas particles had a specific average kinetic energy. At a 0 degrees Celsius, it had a lower average kinetic energy, and as they extrapolated their data, they realized that at negative 273 degrees Celsius, that the kinetic energy of particles was 0. And so that became your new 0 Kelvin. So this is dependent on kinetic energy. I kind of wrote that halfway. And then if you were to add 273 to it, that would be the 0 degrees Celsius. And then if you were to add 100 degrees to that, to the temperature in which water boils, it is 100 degrees Celsius. So whenever we add 273, this is what we get in our Kelvin scale. The Fahrenheit scale is not used very much around the world. It is a unit that is very much of the American unit instead of the metric unit. You should be able to know how to convert between the Celsius and the Fahrenheit, which is the formula is provided in your cruncher, so that would be no problem to you guys. So just know how to do that. Okay. So now let's go on to what we call vapor pressure and evaporation. You guys already know what vaporization is. It is a process of a liquid turning into a gas or a vapor. It happens during evaporation as well as in boiling. But let's now define evaporation in terms of kinetic energy. So evaporation in terms of kinetic energy is that, as you guys saw in my computer simulation, that some of the particles are moving very fast and some of the particles are moving very slow. So likewise, in a liquid, some of these particles in a liquid are moving very, very fast, and some of the particles in the liquid are moving very, very slow. The fast-moving particles, when it's at the edge of the surface of the liquid, it can actually escape the liquid phase into a gaseous phase, and this is what we call evaporation. So after about a day, you come back to this cup of water, you're going to see a little less water than before, and the reason why is because the fast-moving particles have continually just escaped the liquid phase into the gaseous phase. So here is a animation that I'm going to show you in a little bit, but let me describe what you are looking at. Over here is a container with a little bit of liquid. The liquid has, some of its liquid has evaporated into a gaseous phase, and these gas particles are moving around and they are hitting the top of this surface of the mercury. This is a U-tube, kind of like, which resembles your barometer. And this is a U-tube filled with mercury, and inside this space right here is a vacuum, meaning that there are no particles inside. These vapor are causing a pressure against the surface of the mercury here, pushing down the mercury and pushing up the mercury on this side. So the pressure, the vapor pressure of this gas can be measured by the difference in the height of the mercury in millimeters of Hg. The millimeters of Hg can then therefore be converted into either atm or kilopascal, depending on what you are using there. As I'm going to now play the animation, I need you guys to take a look at how the mercury level changes, or the height difference of the mercury level changes, as well as the particles moving in this container, as well as what you understand what you understand dynamic equilibrium to be.
This is an apparatus for measuring the vapor pressure of a liquid at a given temperature. The U-tube attached to the flask contains liquid mercury, which is used to measure a change in pressure. What happens at the molecular level during evaporation? In the beginning, the traffic is only one way. Molecules are moving from the liquid to the empty space. Soon, the molecules in the space above the liquid establish a vapor phase. As the concentration of molecules in the vapor phase increases, some molecules return to the liquid phase, a process called condensation. Eventually, the number of molecules leaving the liquid is equal to the number of molecules returning to the liquid. A state of dynamic equilibrium is reached as the rates of evaporation and condensation become equal. The difference in mercury levels, represented by H, is the equilibrium vapor pressure of the liquid at the given temperature.
So I hope that you guys were able to see that the gas particles were going from the liquid phase to the gas phase at the same time as some of the gas particles were going back into the liquid phase. So because we were not making any more vapor pressure, we knew that no more vapor pressure, the vapor pressure was not increasing or decreasing. So we talked about gas particles having varying speeds. So even in the same temperature, you have some gas particles are moving faster than others. Also in a liquid, we also talked about the liquid molecules having varying speeds. Some move faster than others. Over here, this is another way of explaining evaporation. This is a distribution of the particles. Let's say a liquid particles. So here's a number of particles on the y-axis, and over here, when I say energy, I actually mean kinetic energy. So this is the same thing as kinetic energy, which also means the same thing as the speed of particles. So over here you can see that in a container you have some that are moving very, very fast and some that are moving very, very slow. Over here in a cold sample of water, oh, I can't draw a circle, cold sample of water, you have the average speed being somewhere around here, and this is my average speed of the particles. you could see that even in cold water, there are some particles that are moving very, very fast. And that's why even a cold drink, you would have evaporation of cold drinks, because if I say this is the minimum speed the particle needs to have in order to escape the liquid phase, you have a small population of these very fast moving particles in cold water that can actually vaporize. So if I were to now take this drawing and put it in terms of warmer sample of water, so here is the warm sample of water, the number of particles are kind of swaying a little bit more towards the right side of this chart. So again, this energy is what we call the kinetic energy, which also is pretty much translates to speed of particles. You have more number of particles in the higher speed, and my average speed of particles is a little bit higher. Yeah. The average speed of particles can also be thought of as temperature. So temperature is the average speed of the particles. But now if I draw a line right here, ooh, that's a line. That's my line. And say this is the minimum kinetic energy needed to escape the liquid phase, then now you can see that more number of particles in the warmer water have the speed enough to escape the liquid phase versus the colder temperature.